Welcome to today's webinar. The topic today is optimization of mass distribution for harmonically excited structures in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the content of the website, the German and English webinars, customer projects, newsletters, and so on. I will be the moderator today, and I will answer your questions together with Frank. Andreas Niemeyer will do the presentation, but my two colleagues can introduce themselves.
Hello, my name is Frank Faustich. I'm responsible for quality management and product development in the company, and today I will try to answer your questions.
Hi, I'm Andreas Niemeyer. I'm working for Dlubal since I think 16 years and responsible for the product engineering. I'm taking care about features and program concept, how we perform the features in the program, and then we do it with our programming staff.
Okay, thank you for your introduction. Then we can switch off our webcams that the attendees can see the full screen. I say something about how you can ask questions, at least for the attendees who participate the first time. On the right side of your screen, you can see the control panel. You can show that with that arrow here, and then you can enter a question here. Yeah, and then we will answer you. If you don't get an answer during the webinar because there are too many, you will get an email afterwards. You can also watch the entire webinar and then email your questions to info@dlubal.com. Okay, then I hand over the screen to Andreas Niemeyer. Andreas, it's your turn.
Thank you, Andreas. Okay, then I take over with the topic optimization of mass distribution for harmonically excited structures. In fact, a complex title, I would say. I expected a specific target to explain you something with this example. Especially, it takes care about our add-on optimization, where you can find with a self-learning process parameters what fits for your system and gives you good results. For this, I created this example, of course, with connection to dynamic load, but you will see how you can use it in optimization process. To explain you this demonstration today, I created 5 main points, what we do one after the next. And the first, of course, is the description of the structural task. You see on my right side here a few slides, or let's say plots, what we will do in the next hour. It's a simple beam where we investigate oscillations and then we calculate forces over time. How we can do this in our program RFEM, I will show you in point 2 and 3. We create together this model, make a manual check, then we prepare it for a manual optimization, and later we use this self-learning process, this optimization add-on, to find good parameters. And finally, we give a summary about everything and the outlook, what is coming as next. So now let's go to the first point, description of structural task. A simple slide here. You see, we take care, or we want to model a simple beam with a load in the middle. I sketched up a washing machine, that you have something for imagination. I want to symbolize here that we want to simulate a rotating machine with a specific frequency and a specific eccentric load. And I expect from this, let's say, rotating machine on this simple beam, that this beam will oscillate. Let's say it goes down, it goes up, and it finally vibrate over time. And for this task, we have to check if this beam, let's say with a discrete cross-section and from a discrete material, can overcome these loads. and is stable and works. And later, if not, and this example will give us a sign that it's not okay, what we can do to optimize the structure and to decrease this deflection, what I symbolize with this red arrow. And my idea, or let's say what I want to show you is, of course, we can change cross sections, supports, loads, but I want to try to place additional load on the member to, let's say, to decrease the deflection. What sounds in the first instance strange, to bring up additional load to decrease the deflection, but you will see how it's connected. For this, I use these dynamic functions because here you can simulate such effects. Okay, now this is the point where we change to a live demo, where we jump into the program, where I can show you how this could be done. So I open RFEM. I already prepared it. The program wants to know from me the file name. So let's give this child a name, Duno 10, for example. We use a 3D model, and later we have to specify the task, because we want to simulate here in the next a rotating machine over time. In the program, we have to activate the so-called time history analysis with all following add-ons like modal analysis. Further, we have to check if the beam can carry the loads what we apply. We have to select a steel design. This is for my demo enough. We check the steel design according Eurocode, basic Eurocode. Of course, we can select any standard, US, British, Chinese, whatever, but I use this basic setting here. If we jump into the program with a confirmation of this dialog, it will open, let's say, an empty RFEM environment where we see our 3D space, navigator, table, and bottom, and we can directly start modeling this structure. Let's say, of course, it's an easy structure. I would say we place this beam in this XC or on this X direction. So I use a function new member. Let's use here a new section, and I select for this beam an IPE 360, for example. So this I meant with discrete cross section from this Euro standard with a steel S235. So this settings describes, let's say, the stiffness of the beam, and I pick it, and I made it pretty easy for me. I select or I want to simulate a 10-meter long beam, so I only can pick the grid points on the bottom. In the next point, I have to define the boundary conditions. The first one, let's say the supporting conditions, we doing over types for nodes. So let's say node 1 is supported in X, Y, Z, and fix also the rotation about X, and the other two are free. The node on the right side, node 2, is open in X, rotation is fixed, and the others are free. And the remaining settings we can delete. So now, if we take a look on this structure, what we just modeled, we see simple supported beam, and the program already specified a load case self-weight, because it thinks it's used from civil engineers, but always have to work with self-weight. If we want to display this self-weight, we can activate it here, and we could wonder why we don't see something, because that's because RFEM thinks the self weight of the elements itself is, let's say, boring because it's always here. So it's deactivated in standard that you can activate here in Display Navigator. And you see our 10-meter long beam have here, let's say, a self weight load of 0.571 kilonewton per meter, what results in a weight of 571 kilograms. No? And additional to this weight of the beam, we have now the weight of the machine in the middle. How we can apply it? I would say we simulate it as nodal load. So I divide this beam into two parts, divide member, intermediate nodes. I use one division with one element, and I get finally two beams with one node in the middle, where I can apply the weight of the, let's say, machine. I estimate from this washing machine it have a weight of 100 kilogram, so I use 1 kilonewton into the direction. So let's select this node and we get additional this force. And if we calculate now this load case, we will get, let's say, a deflection and a force in the beam, which corresponds to the, let's say, self weight what we specified. And you see, if I apply the weight of the beam plus the 100 kilogram in the middle, we get a deflection of 0.3 centimeters. Of course, besides this deflection, we get also here forces and also stresses, maybe the sigma stresses, what we can visualize with compression and tension on the bottom. But this is now minor. When we want to know is this deflection and force now okay for the beam or not, we have to do a design. For this, we have to learn the program what he should check. Of course, the cross-section is fine, but if we want to check also lateral torsional buckling and such stuff, we have to define some stability informations. So I take both beam elements and glue it together with a member set, create member set. And here I can define that we want to design the member set itself. So we see full length of both elements. And in this tab, we can now specify the stability settings. So we say, please consider it in an effective length. So for me, it's a buckling check, what I assign to the member. And here we give the full program. So check about buckling, about Y, C, torsional buckling, lateral torsional buckling, everything is activated. And we say, please make a pin support on start and end. And I check this, and now the program knows everything what is important for a ULS design. And for ULS design, the program needs finally, okay, which load should be designed. You have to know if you start RFEM, it always thinks like a civil engineer. It thinks you want to combine loads according any standard. Of course, we can do this now, but this is not the focus of this demo. So I only want to have a characteristic utilization according to the load what I define. Therefore, I turn off all this stuff. Define this load case should be checked with self weight according ULS state. The SLS states we deactivate because they are not interesting in this check. And further, we say, okay, please make a load combination according linear analysis. And here the load case self weight should be considered. In reality, in real life, when we have to consider safety factors, here would be, for example, 1.35. But here I select only the load case without safety because to have comparable results for demo. Now, everything is done and we can run a steel design. And you see the program is calculating first the, let's say, load combination, and then it feeds the steel design add-on, and you see, okay, our steel design results in 0. or let's say in 12% utilization. When we want to know what is the most worth, we can here open the table ratio by members, and you see section proofs are all fine, and the stability check is maybe the most crucial here. Of course, only 12%. You get here a hand calculation and see, okay, the existing or the acting bending moment is smaller than the resistance, so everything is fine. When we speak about stability, you see also here a buckling curve, or let's say, buckling curve. And to make it more visible, we can also render here the deformed cross section, and you see this is the shape for the critical bending moment of the design check. So now everything, if you see this picture and this utilization, I would say everything fine. Yeah, design is made, of course, also when we add a safety, but let's say a small but, and therefore I prepared this example. What happens if we turn on the machine and simulate here an eccentric mass? Let's say it's a washing machine, so I estimate 10 kilogram eccentric mass with eccentricity of 20 centimeters, because the drum have a diameter of 40, and I simulated with 800 rounds per minute. So it's not the full speed of a washing machine, then more the lower speed. But let's see what happens if we do this. And for this, when we talk about rotations over time and excitation, we have to know that structures have eigenfrequencies according its mass distribution. And first of all, we should take a look on these eigenfrequencies to see, is there an eigenfrequency here what is crucial for our load direction. And therefore, I open the table load case and combinations, go here into the second line, I double click that I get the dialog for defining the data. I write here as load case name, modal analysis. And now this is a quite special setting, because generally everybody thinks load case means something with static, but you see you have here a box to select something. You can also say, no, it's not a static analysis, it's a modal analysis. And if we talk about modal analysis, we need new calculation settings, something else than a static analysis setting. And we open this setting and see, we can define here number of modes what we want to calculate. Just depends on degrees of freedom, but generally I don't know which number I should write. But RFEM gives you an option. You can select here automatic to reach an effective modal mass factor bigger than what you define here, for example 90%. To use this option, you have to use this solver root of characteristic polynomial. And further, we do now some simplifications, because as mentioned in begin, we only want to describe the phenomenon. Therefore, I say, okay, please simulate this oscillation of this washing machine only in vertical direction and around Y direction. And this we confirm, and we give the program the information that it should take for this modal analysis the masses from our load case 1 self-weight with the 571 kilo of steel beam plus 100 kilo of the washing machine. Now let's run this analysis, not load case, and let's say in brackets analysis, where we get now not bending moments and deflections, and we get modal analysis, let's say oscillations without dimensions. So the biggest amplitude is here 1 without a unit, and we get here on the bottom a table to to this shape with the eigenvalue. So you see we have here a bending shape with 10 Hertz. We have a harmonic of this with 47 Hertz and with 90. So this is the oscillation. The program needs 3 eigenvalues to fulfill the 90% of mass what we specified. And this says me also what is really interesting, the most governing eigenfrequency moves this point where the washing machine is standing as most. Now, therefore, it could be interesting. We see we have here a little bit more than 10 Hertz. And when I speak about the washing machine with a rotation of 800 rounds per minute, and 800 rounds per minute is translated into Hertz, 13 Hertz. So we speak about 10 to 13, so it's in between these two frequencies. We know, okay, it's close, but we cannot decide is it crucial or not. We have no idea. We only have an RFEM, and RFEM allows us to calculate these shapes. So let's go on and try to simulate this rotating machine. For this, I go again into the load case list, define a new load case, define a name, washing machine. Define here analysis type. So we have now to do something over time, how it reacts over time, not static in one time point. So we select here time history, analysis, time diagram. We specify the calculation parameters. The calculation parameters, when we calculate something over time, we have here two options. We have, let's say, I call it always envelope method, a linear modal analysis, or a direct method. I use the simpler one, the easier one, linear modal analysis, where I give the program the command, please do the analysis, let's say, over 4 seconds. So please calculate results from 0 to 4 seconds. Further, if we do such a calculation, we have to know it's a numerical system. If we have a vibration in the program, it never ends if we have no damping. So I give the program the information. There is a specific damping from your structure, what makes the oscillation smaller over time. You can select here from a relay damping and a Lersch damping. I use a Lersch damping based on 0.1 as logarithmical damping decrement, and if I transform it into a Lersch damping, it results in a number of 0.016. It's a typical model relevant data. It depends really if you create it from steel or from timber or concrete and how your connection is made. So which energetic dissipating systems you have. So it's a model information what you feed here. And in the next point, the program wants to know, okay, what is my model shape for what I should do this analysis? And I select here, of course, please use the model analysis what we just made in load case 2. And for me, is this washing machine a live load, so I give him a red flag. Now, this was everything about properties of this load case, but still nobody said how quick or how fast the rotation is, how heavy. So all these things we have to still to define. Let's do at first the reaction over time. And you see, the program wish to get a time diagram. In x-axis we have the time, and in y-axis we have a escalation factor, and the escalation factor or multiplication factor multiplies the load what is in this load case 3. So let's open it, and here we can define this time diagram by a table, of course, but I would say for a harmonic excitation or harmonic activation, it's boring to make it over table. So let's use here a function. And the function is pretty easy. So you can write here cosinus, bracket, maybe omega. So here's the circular frequency, maybe 1 multiplied with the time. And if I close the bracket, you will see you get here this oscillation. As more you change this maybe circular frequency to 2, you see you can change the art of oscillation and also activation. In our case, we have to rate in this figure the circular frequency of the washing machine. We know 800 rounds per minute. Yeah. So let's write it here. It's transformed in this circular frequency format. If you write it P multiplied with this frequency of no, let's do it different. Let's write omega. No? Then you see it directly. Omega. And now if I confirm it, the program don't know what should I do with this omega. But we have here such a formula control where we can write, okay, we have rounds. It's a integer value. So we can use it here, maybe model ratios, no, integer, and we have 800 rounds per minute. And now we can calculate a circular frequency, so I call it omega. And I give this omega is a unit group, or let's use here a float value. And we write this is not the value what I give, then I calculate it by a formula. And I can write here this is P multiplied with rounds divided by 30. And if I do this formulation, I get the circular frequency here in this field. And if I confirm it, the program gets this omega, this figure to it, and you see it changes. And if I say now, please calculate over 4, or I need this diagram for 4 seconds, we have now the diagram for which we multiply the load over time. Now, this is fine. We have this function. We can also give here a name, maybe here a washing machine. And now we have only to rule for which forces we want to use this diagram. And this is now really easy. Let's say we say, okay, this load, what is inside the drum of the washing machine, let's estimate 10 kilograms with this eccentricity of 20 centimeters. We can calculate something like a centrifugal force in this direction where we want to exit this structure. So let's use here a nodal force in C, and we can use here now our parameters what we already have. So we have 10 kilogram eccentric mass. Let's write the unit multiplied with 0.2 meter eccentricity and multiplied with omega with power 2. Yeah. And if I define this, the program calculates me 14 kilonewton. This is the force what is now, let's say, according to the diagram what we just defined, going up and down according to the frequency what the 800 rounds per minute defines. Yeah. And now we can run a first analysis only for this load case, and let's see what means this activation if we have an eccentric force in this machine by this frequency. And you see it takes a little bit longer because we calculated over time for these 4 seconds. And now we get a deflection downwards and upwards. So this is an envelope, and we see we get a deflection of 2.3 centimeters. So 2 centimeters more than the pure static effect. Yeah. Of course, you can see here the results over time, how the deflection increases and jump from bottom to top. But this is, I would say, yeah, hard to understand. In this case, I recommend you to use the calculation diagrams. Go here to diagram type, basic, time history analysis for load case 3. And please check the UC value for the, let's say, the node in the middle. So let's select it. And you see now how the deflection is changing over time for the 4 seconds. So in begin, we start small, then we get a big activation, and then we have a leveled result here after a few seconds. And now, the only point what is now, this is only the eccentric load, but no self-weight is considered. So we have to envelope both. And for this, we jump into the load case control, go to load combination, change this load combination from a static to a history type, use the settings what we used before. And in the assignment, we have now the self-weight plus washing machine. So I can envelope both. You see we have here a column for diagrams. Of course, washing machine we defined, but the self-weight needs a diagram. The question is, which diagram have a self-weight? Yeah. In my case, I would say it's constant, but that it don't changes my system too much. I say, hey, program, please simulate the self-weight slowly on the structure. So let's say increase it within the first second slowly to a level 1, and then the further 3 seconds please hold it on level 1 and go ahead constant. So we increase the self-weight slowly to 100%, and then we hold it constant. And now we have 2 loads. The first is constant working, the next is oscillating, but starts 1 second later. Now we have this load case, and for a design, we give this load case into a result combination where we say, please design this result combination with these enveloped results. And now let's check what happens if we do a steel design with this rotating machine in the middle of the beam, if it's still okay or not. So this is the combination, calculation of forces and deflections. And this is the steel design. And now it could come as expected. In the middle, we get a red flag. We see we have a utilization of overutilization of 10%. So maybe if somebody wonder what is crucial, let's go to the checks, and you see stability check is critical. If we open details, now the acting force is bigger than the resistance, and this means we get no okay for this beam. Also, the pure static check was okay, but the dynamic force is not. If we want to see the diagrams, what happens? So let's make a new diagram, type time history for this combination, what we just did. For you see we increase in the first second the self-weight, and then we apply the dynamic effect, what is leveled here in later seconds. Yeah? But we have here some peaks, and this leads to a bad design. So now what we can do? We can increase cross-section. We can change supports. We can reduce load. We can place the washing machine here on this place. Several options, of course. I proposed in begin we can apply some additional loads. Of course, at the moment we're fighting with 2 big deflections. So this combination gives us a deflection of 2.56 centimeters. So is it really a good idea to apply additional load? Could be or could not be. Let's try it. For this, I divide these two beam parts into new separate elements. So I divide it with 4 nodes and change in the load case self weight here the loading, and I apply maybe 50 kilos, so 0.5 kilonewtons on these nodes. Okay, and you see we have now another self weight, and if we run design again with this new loading, let's see what happens. What is cool and what you should see also from this demo, you can change everything afterward. You only have to recalculate. So if you hard code it in the program, the design, everything is clear what to do. So the design settings all is dynamic and adaptive to your settings what you give. So it's really easy to change the nodal loads. So now what happens? Our red flag is gone. We have a utilization of 0.59, what is fine. The deflection, I think, is also a little bit smaller. Let's check it. It's now 1.4. So it's working. If we apply in this case with this, let's say, resonant activation or almost resonant activation, a little give another mass distribution, the system is going to be better. So we bring it out of tune of this resonant effect. Of course, we cannot increase these additional loads extremely, because then at any point the standard deflection of statical effect is too big. So there is a optimum of this mass distribution what don't bring additional deflection, but reduces the utilization. And the question is now, what is the best value? Is it 0.5, or let's say we don't know it? And what happens now? In reality, this is exactly the point where you, let's say I make it a little bit easier here. I hide this. This is exactly the point where you try something and then you think, okay, let's increase it a little bit or decrease it a little bit. So we can select all these 0.5 forces and change it. For this, you can use, for example, also a manipulation factor. So we can also bring in here a factor M. Say this is a force. I don't know. And let's write here 0.8 to try if we increase it a little bit. And now we say these forces are nodal loads, edit, have no figures, and they connected to a parameter is M. And it's easy to change it and to recalculate it. Now you can, it's a try and error to find the smallest utilization with the best weight fit. Yeah. And this is now the point why we are sitting now together. For this job, we added the optimization add-on. And the optimization add-on is hidden here, where I said in begin, I activate it later. You can activate it here. And this is not a static calculation or any design. Or it's a really special add-on what allows you to do some special tasks. And if you use this optimization add-on, you get in this parameter list, this parameter what we just defined, new types. You see, you have here now 3 new types optimization. And you can say now the optimization, maybe the starting value, let's start from a really small value, should run from in an interval of 0.01 to, let's say, 8.001 with an increment of 0.2. What means finally we have 40 steps or 41 solutions. And this is now a range where we change this value. And if you activate this optimization, you get below calculation, optimization settings, where you can now define, please store the best 20 solutions. So if what is a solution? It's a solution or mutation in our words. It have nothing to do with X-Men or something like this. And mutation is variant with 0.01, variant with 0.5, variant with 8.001. So the model with the changed load. And now what leads to a best solution? So you can find models with the minimum weight, with a minimum deflection, minimum cost, minimum CO2 emission. So we use minimum displacement. And here you have now, let's say, a robotic function what checking all 41 solutions according your interval of this parameter what you defined. Yes, is a cool function. What is doing for us is change automatically and finds us the best solution. But you have to know such a calculation run takes around 23 seconds. If we multiply it with the factor of 41 mutations, it ends up in around about 16 minutes. 16 minutes is okay to find a good solution and to save time and money, of course. But you also have to know if you have more parameters. For example, we say these loads could be different. Then it ends up in millions of mutations. And then you can ask the question, do I have to calculate all or only a fraction of it? And a fraction of it is now hidden here with this option particle swarm. And the particle swarm is now, you see, now the program asks you for a % of mutations. Is now a method where I only calculate a fraction of it, for example, 50%. So I calculate 20 mutations and expect to get a good setting for this value m to fulfill my demand, a minimum displacement. How is this working? It's working because the program is starting with a random set of parameter m. And the second random set also. So the first two more or less random selected. Then, according to the first two solutions where it realized, okay, with my first random selection of m, I get a displacement of 5 centimeters. In the second, I get a random selection only 3 centimeters. So I know if I change my value in this direction, it's going to be better. Yeah, so it learns from its previous experiences to change the value in any direction. And this process is now made not only for one parameter, and you see it could be a table for more parameters. And now I don't want to calculate because I don't want to use your time for this. I prepared it. If you I confirm I can open here a model. Here is this P start. Here I did 50% of all possible mutations. The program found, let's say, a solution here with 1.1 centimeter deflection, and the utilization was 0.48. Yeah, so this was the smallest utilization we could find by using only 20 mutations. So the program found out, okay, during its calculation, you see how he worked, and the best fit was if the parameter is 1.4, so we have to add 1.4 kilonewton at every point, and then we get the smallest deflection with its connected utilization. If we watch this reaction over a diagram, so I defined here a diagram, you will see if you calculate only 10%, so 4 or 5, the program finds a solution bigger than 1.4 centimeter by using maybe 1 minute. Yeah. If we calculate 20, you see the deflection is going down, and by 40, 50, you see we come to a minimum, so to this 1.1 centimeter by using 6 minutes roundabout. This is the orange line. And if you calculate all 100%, so these 41 solutions, you have to invest 60 minutes, but you don't get a better result. So this particular swarm optimization saves you time and gives you better results or structures where you can save material and whatever. So this is not a method what you can use for really huge models, and it's made for finding a good structure or partial structure in a big building where you say, I don't know, should I increase the height or the width or both? And the program helps you to find a decision about by not using 100% and only by calculating a fraction of it. And this is maybe what I want to show you, what we made regarding a self-learning process inside the program. And this is only the start what we are doing. So we prepare our program with more such, let's say, artificial intelligence functions. This is the add-on function, but additionally, maybe you see also here such a chatbot where you can ask questions, and this questions is not only a stupid database, then it knows our database and can create from this stuff what we write here inside, maybe all manuals or FAQ, frequently asked questions about all knowledge base articles, a good answer for you. So I can ask here a question, any format where I can define masses, can define masses in RFEM 6, then the program is thinking and using its data, what is behind, and giving you a feedback. And if it's possible, it gives you also a source where you find more data to this answer. Yeah, and we wish, or let's say we think this function could help you really a lot, saves your time to be quicker than in any other software. And this is now maybe the end of my presentation, and I give back to Andreas.
Okay, Andreas, thank you for this nice presentation. Yeah, I would like to show you where you can find the recording of the webinar and the model. But before I do that, I would like to present you an offer. I hold back the screen. Okay, you should see my screen. If you want to get a free online product demonstration, just book a free online appointment. Contact our sales team with that link here, or you can scan the QR code. Or if you want to get a non-binding offer, then you can also contact our sales team. So now I show you our website, and dlubal.com, and under news and events, you have to go left to the events, and then you can find the webinars. Those are the webinars of the next week, or next weeks. Most frequently asked questions, our regular webinar. I will present that with together with Jürgen Teilmann. Then in the week after next week, we present the API to Python, then linear stability analysis, and so on. I have to scroll down to the past webinars. Okay, that's already a past webinar we are at the end of the webinar. Okay, yeah, in the next days you will get an email with a direct link to that page here. The email will contain your attendee certificate, and on this page you will find the recording in the middle here. You will find or you can already find the presentation slides of the webinar and the model to download. Yeah, that's the simple model with all entries that Andreas did in the webinar. Okay, that should be also all from my side. Thank you for your attention. Thanks to Andreas for the presentation. Thanks to Frank for the support by answering the questions. I hope we meet each other in a future webinar. Yeah, have a nice rest of the week and bye-bye.